Hi there students, this is Dr. John coming to you today with another introduction to trig functions. Today we want to talk about where we get the secant function, where we get that name from specifically. To do that, we're going to start off by reviewing briefly where we get the sine, cosine, and tangent functions. And as I've mentioned before in a number of videos, that a lot of what we do with trigonometry is based upon what the ancient Greeks did. They love to draw triangles inside of circles. So that's what I've done for you here. I've drawn this inside a unit circle. Notice the radius of the circle, it's 1, 0 here, 0, 1. That means the hypotenuse here, the hypotenuse is equal to 1. The entire radius of the circle is 1 here. I picked an angle 60 degrees just because I can calculate the sine and the cosine, or the x and the y values. If you remember here, this x value here, which is the first value here, is the cosine value, and that happens to be 1/2 for 60 degrees. And the sine value, which is the y value, is √3/2. I have those calculations for you on the unit circle on another video, or you can just check them on your calculator. So if this is the cosine, this is the cosine value here, and this is the sine value here. To get the tangent value, we would take the sine over the cosine, so that would be √3/2 divided by 1/2. We would flip this, make this 2/1, and multiply. Division is just flipping and multiplying. This cancels, we get √3. So that means the slope of this, or the tangent value, is √3. Tangent of theta is equal to √3, which is also the slope of this line, because it's rise over the run. Now, as to why they're called sine, cosine, and tangent, remember in another video we talked about how the sine value, notice here, it comes over here in the circle, and then it comes down all the way. You could continue this on and cut the circle right here, just like I'll draw here. So a line like this that goes like this and cuts the circle in 2 places. Could be any 2 places. Could be those 2 places. This line over here or this line over here, those are called chords. Not the word cord like this, which is a piece of rope, but chords like this. A chord is the line that intersects a circle in 2 places, but it's inside of a circle. Now, we get the word sine from the ancient Sanskrit, had a word for chord that was mistranslated into Latin as the word sine, and then translated into English from there, where we get our English word sine. So our English word sine is sort of a mistranslation of an old word for chord. Hence, this chord here, similar to this blue chord here, is like half or double the value of the sine value. So that's where we get the word sine from. The word cosine is the fact that it is a complementary angle to the sine. And the word tangent, and that sort of comes from this. If you think of this circle here, and I'm going to draw a tangent line to this circle. What a tangent line means is this. A tangent line would touch the circle at exactly only one spot. So that's that spot right there. So this would be a tangent line to the circle, which is a different word than the tangent for this angle. The tangent for this angle is the slope of this blue line. This green line is the tangent to the circle. However, if you remember from geometry, if you have a blue line like this, and then another line like this that is at 90 degrees to it, the slope of this line is related to the slope of this line. In fact, the slopes of these 2 lines are flips of each other and negatives. Because if this one's positive, this one's obviously a negative. And you notice the bigger the slope gets, the smaller the slope that this one would get. I'll give you a specific example. Let's say we had something here that had a rise of 2 and a run of 1. That means the slope would be 2/1 or 2. So this line here would have a slope of 2. If we wanted to draw the thing that was at 90 degrees to it, we would go down 1 and across 2 like this. So we would be this. These would be at 90 degrees to each other. The slope of this one would be a rise of -1 and a run of 2, or a slope of -1/2. So notice how the slope of this is 2, slope of this is the flip of that, or 1/2, but it's the opposite sign, so it's negative. So the same thing over here. If the slope of this line over here, which is the tangent function, that is related to the slope of this line, which is a tangent to the circle, and the slope of this one actually, m for slope, is -1/√3. So the idea is this, we call this the tangent function, because the value of the tangent function is related to the tangent of the circle itself. It's related to it by being flipped and negative to it. So that's where we get the word the tangent function from. So hence we have the sine, cosine, and tangent. Now we're coming over here. We have the reciprocals, or the flips in the denominator, where we put this in the denominator, 1 over sine, 1 over cosine, 1 over tangent. How do we get these names? Well, this one here looks like it's a complementary angle to this, fairly straightforward. This one here, if you notice, this is a so this cosecant is a complementary angle to the secant. So what we'd like to do is figure out, where do we get the word secant from? So as I mentioned before, the ancient Greeks loved to draw triangles inside of circles. So we've done that, and then they would draw various lines and seeing lines and other circles to see what might intersect, what interesting things they might find with that. So if you look at the sine here, this line here that has the sine, if we continue that on, it doesn't really intersect with anything interesting. But if you take the cosine line here, which is this line, and continue it on till it hits here, till it becomes a chord, and then continue that line onward, notice how the tangent of the circle here intersects with this line that continues on from the cosine. Now, what is it called when a line continues outside a circle? Remember I said this line inside the circle here is called a chord. But if the line continues outside the circle, this is called a secant. That's one of the definitions, it's one of the names you may need later on, not relating to trig functions, but relating just to definitions of a line. If you have a line that hits a circle in two spots, any two spots, it can be straight up the diagonal, like the x and y axis. The x and y axis are secants of the circle as well. So once it goes outside the dots, the center, once it goes outside the circle, it becomes a secant. When it's inside the circle only, it's a chord. This line here that continues on from here all the way over to here, once it's past here, becomes a secant. So we can call this a secant. So the next thing they would ask is, so what is this length? Is this length anything interesting? This length from here to say here. Well, can we calculate that length? Well, there's an interesting way we could calculate that length. If we could find the equation of this line, we would just have to set that line, the y equal to 0, we could find the x value. So let's see if we can calculate the equation of this line. So you might remember from your basic line equations, how you get the equation of a line if you have one point. And what you do is you take a generic y value, I just wrote a generic x and y value here, subtract the specific one, root 3 over 2, there you go, divided by the generic x value minus 1/2. And that's going to equal your slope, which is minus 1 over root 3, just like that. So now I've got the rise over the run is equal to the slope. I can simplify this just to get y equals to something. So let's take this value over here and multiply it by both of these terms here. So here's the next step. I've still got this here, y minus root 3 over 2. I've taken this over here, so that's minus 1 over root 3 times x, and then double negative, so it's plus 1 over root 3 times 1/2. Well, I have two terms here that involve just numbers. I want to move them to this side, and I will do that right now. So I'm going to take this here, which is root 3 over 2. That's this, move to this side, plus 1 over root 3 times 1/2. And how do you add those up? Well, for one, what we'd like to do is we would like to have this in the same form, which means I'd probably like to have a root 3 here in the numerator. I could change this by multiplying the top and the bottom by root 3. So I'll do that, and I'm going to get root 3 on the top and 3 in the bottom. Now I have this times this, which is 6. There you go. So I've got root 3 over 2 plus root 3 over 6. This could be multiplied top and bottom by 3 root 3 over 6. So adding these up, I get 4 root 3 over 6. Cancel that with that, and I get a 2 over 3. So I'm going to be left with 2 root 3 over 3. And if I wanted to, again, I can divide this out and make this 2 over root 3. It's a lot of mess there, but that's what these two terms add up to. 2 over root 3. Y is equal to this first term minus 1 over root 3x. And then these two terms added up, which is plus 2 over root 3. That's all of this now. Now I've got an equation of a line, a nice pretty equation of a line. What I want to know is, what is the x value here, all the way from here to here, when y is equal to 0? So if I set this equal to 0, I can move this to the other side, and I get 1 over root 3 times x is equal to 2 over root 3. I can cancel this and get x equals to 2. So in this specific case, I have x equals 2. And if you remember here, the cosine here is this value, it's 1/2. So notice this value here for this secant is the flip of this. If you remember before, the cosine, if we want to flip the cosine, that would be the reciprocal. So this looks like the reciprocal for the cosine, but let's do this for a general, not just a specific value of 60 degrees. Let's do it for a general value. So I'm going to erase a few things, come back and really quickly do that as well. So let's go over this general case where this value here is AB. We don't know exactly what it is, and the angle is theta. Well, in that case, since this one here is the cosine, and this one here is the sine, the slope of this, the slope of that, which is the actual tangent function, will be b over a. Which means this one here, which is the flip of it, and the negative flip of it, the slope of this one is going to be negative a over b. It's flipped and it's negative. So that's the slope of this line. We have a specific point, AB, and we have a slope. So let's do the calculation of the line. So the point is AB, the slope is negative a over b. We go like this, y minus b over x minus a is equal to negative a over b. Now we cross multiply, this times this times this, and I'm going to get by minus b squared, that's this times this, is equal to negative, I have to have the negative somewhere, so I'm going to keep the negative with the a here. So it's going to be negative times the negative, it's going to be positive a squared, because I'm going to keep the negative with the a, not with the b. So that's a squared, and then it's going to be minus ax. So those are the four terms. Let's move this b to this side here, and we're going to have this equal to minus ax. I just moved this term over there, plus a squared plus b squared. That's this term over here, and I'm leaving this by. So there's no difference here. There we go, I don't need any of this. Now if you notice here, this is a squared plus b squared. Well, that happens to be the cosine squared plus the sine squared, or this value of the triangle squared plus this, which is 1, which is the hypotenuse. So a squared plus b squared is equal to 1 for any right angle triangle. Or this is also Pythagoras' theorem for angles. So it means this here is equal to 1. So I can erase this and make this just equal to 1. Now divide both sides by b, and we get y is equal to negative a over b x plus 1 over b. If I want this, I want the value of x when y is equal to 0. So I want how far x is here. So I will just make this equal to 0, like that. Since I have a negative over here, I'll move that to the other side. A over b times x is equal to 1 over b. Multiply both sides by b, and I get this. Divide both sides by a, and I get that. So x here is equal to 1 over a. I notice the value here, the cosine value is a. So the cosine value is a. This value here is, for any value of cosine, is 1 over a. So that is a true reciprocal for the cosine. Hence, we call the secant the reciprocal for the cosine. So here I've really quickly written the three standard trig functions, sine, cosine, and tangent. So that we start with the sine because that's a chord, and then this becomes the complementary angle. This is the slope of the circle, the slope of the line up to that point, or it's related to the tangent of this line, which is, of course, it's the reciprocal, the negative reciprocal of this tangent line here. So that's where we get the names of those three. And then the secant, which is sort of like the beginning of the reciprocals, comes naturally from the definition of secant. We're just using that word, and it comes out from the cosine in a natural way. So we make that as our starter. The cosecant, this is the complementary function to the secant, and then the cotangent here is both a reciprocal and a complementary function to the tan. It's the only one that does that. It does both at the same time. So I hope that helps you to understand the secant a little bit better. If it does, like and subscribe. I will see you in the next video. Bye-bye.